are Shades of Science. Hi, my name is Jody. Hi, I'm Chelsea.
Hi, my name's Adam.
Hi, I'm Belle.
Hi, I'm Charlene.
And we are doing an experiment that will investigate how different colors of water absorb thermal radiation.
Imagine it's a sunny day. You and your friend are wearing different colored clothes, dark blue and light green. Your friend in her dark colored clothes is hot from the sun, but you're not. This is just one example where heat transfer principles appear in everyday life. Most people wear light-colored clothing in the summer, but why is that? This is because darker colored clothes absorb more radiant energy and therefore tend to experience greater temperature increases, while lighter colors reflect a larger portion of the radiation and heat more slowly. Understanding which colors are most effective at absorbing radiation has real-world applications, such as in energy-saving technologies, including solar energy collection, building design, and heating and cooling systems. These applications relate to sustainability, influencing how future structures and materials can be optimized to manage heat more efficiently.
So let's prove it. Today we're running a super simple but really cool physics experiment. We're going to see how different colors of water heat up in the sun. What you need is 4 mason jars, food coloring of your choice, and a thermometer gun. That's it. Very easy and simple, something that you can totally try at home. So let's start by setting up round 1. We added 2 drops of food coloring to each jar, and for our experiment we chose black, blue, red, and yellow. Then we mix all of our jars really well. This makes our dilute set of colored water. Now we have to measure the initial temperature of each jar using the thermometer gun. This gives us our starting point so that we can later figure out how much the temperature changed for each color. Initial temperature was at 20 Celsius, and after that we can leave it for 30 minutes. And after that we can measure the final temperature of each jar. We can see here that our black colored water experienced the greatest temperature increase. But wait, what if we made our solutions more opaque? Make any difference? Let's see. Now we're going to repeat the experiment, but this time with more concentrated color. After repeating the same exact steps as before, we can now measure the final temperatures of the second set. And so what did we find? We saw a greater change in temperature for the more concentrated solutions, and the black water showed the biggest temperature increase overall. This matched our expected outcome and what physics tells us.
When considering radiative heat transfer, it is governed by Stefan-Boltzmann law of radiation. This equation tells us exactly how much power an object absorbs or emits. The P is the net radiative power, which is the energy per second the jar of water is absorbing from the sunlight. Then we have factors that are constant that is being controlled through our experiment. Sigma, the Stefan-Boltzmann constant, A, the surface area, and then the temperature difference between the sunlight and the jars. Lastly, we have epsilon, which is the emissivity. From this equation, the Stefan-Boltzmann law tells us that the power absorbed is directly proportional to emissivity. But what is emissivity? It is the measurement of how well an object is able to emit radiation compared to a perfect emitter, which is a black body. A black body absorbs all electromagnetic radiation that falls on it, reflecting none, and then re-emits the energy as thermal radiation. Its emissivity is equal to 1. But they don't really exist. So for this experiment, we settle for black water where the emissivity is close to 1, which will make a greater absorber. As for the color water, they have emissivity values in between 0 and 1, depending on the color. But how can we know 100% sure that the temperature difference is only because of color? This is where mass transfer comes in. Given the heat capacity equation, we kept the mass and material for all the jars the same, making it constant, which shows that the temperature change is proportional to the Q, the total heat energy absorbed. We also know that the energy being absorbed is equal to P multiplied by time. So if we rearrange the two equations and remove the constants, we find that temperature is proportional to emissivity. So any difference in our temperatures measurements is solely due to the different colors' abilities to absorb radiative energy.
The light from the sun and resulting radiation must be considered when engineering outdoor structures. This is why architects and urban planners sometimes purposely choose colors to best fit the surrounding climate. In warm, very sunny weather, for example, they may select a lighter color in order to reflect the sunlight and generate some cost-effective cooling without wasting energy on AC. In colder climates, a dark roof can absorb much more heat, and similarly reduce the amount of work needed to heat the home. Using these principles another way, solar panels are designed with dark colors in order to absorb a large fraction of light and convert that into electricity more efficiently.
A short summary of our project, Shades of Science. In this experiment, we tested how colored water absorbs heat from the sunlight, and we used mason jars filled with water and added different food colorings at 2 concentrations. All jars stay under the same sunlight for the same amount of time. So our goal was to see how color and opacity change the way water warms up in natural light. So our results showed a clear pattern, and darker colors absorb more heat and reached higher temperature. Samples with more dye or higher opacity also warm up faster. But the lighter colors, like yellow, showed the smallest temperature rise, and these simple tests helped us see how color affects the heat absorptions in everyday situations. It also connect to the real-life examples like Belle just mentioned, like roof paint, the building materials, and the solar energy design. Thank you.